All right, solutions by definition have variable compositions. So in order to describe a solution, you need to describe what's in it and how much is in it. You can do that in a qualitative way by using the words dilute for when there's not a lot of solvent and concentrated for when there is a lot of solvent. Or in chemistry, we use units of concentration to give a number for the amount of solute in a given amount of solution. Except there's one that we'll talk about that's the amount of solute in an amount of solvent. And we can indicate concentration using square brackets. So if you see a chemical with square brackets around it and then a number, that's going to be read as the concentration of, in this case, sodium chloride. So let's talk about different units of concentration. And just remember that solute dissolves in solvent to form a solution. The first concentration unit we'll talk about is mass fraction or weight percent. And then related to that is parts per million, parts per billion, and parts per trillion. And the mass fraction is simply the grams of solute divided by the grams of solution. So grams solute divided by grams solution. And that is, the grams of solution is just the solute plus the solvent. That's related to these other ones. So a weight percent or mass percent is just going to be that fraction times 100%. And then when you get into lower concentrations, so these are often used for, say, water purity purposes, that sort of thing, you can multiply your mass fraction by a million, a billion, or a trillion, and that would be your parts per million, parts per billion, parts per trillion. Next, we have the mole fraction. The mole fraction is simply the moles of solute divided by divided by the moles of solution. And again, solution is solute plus solvent. There, we've run into mole fraction before when we've talked about gases. Molarity, we have also talked about before. It is the moles of solute divided by the liters of solution. And it is commonly used when dissolving solids into liquids, so aqueous solutions. And it is slightly temperature dependent because your solution volume will change with your temperature. Then our last one is molality. We use a lowercase m. In this chapter in particular, you need to be very careful about what m you're using. So a lowercase m is going to mean molality. Uppercase M is molarity. And if you want to say moles, I would write out the MOL like I did up there. Molality is the one that uses solvent instead of solution. So molality is the moles of solute divided by kilogram of solvent. It's the one that's most different from the others that we talked about. And it is used for colligative properties, which we will get into later in this chapter. How do you prepare a solution? You need to know both the amount of solution that you're making and the concentration. If you're going to prepare it in a lab, you want to start with the mass of solute. So start with your amount, use your concentration as a conversion factor, and then you need to take whatever mass of solute you weigh out, dissolve it in enough solvent to get to your total amount of solution. You never want to, if say you're making 100 milliliters of something, you don't want to measure out 100 milliliters of water and then dissolve your solute in it, because that solute will take up some volume. So let's work through an example of that. How would you prepare 250 milliliters of 19.5% by mass calcium chloride? And the density of that solution is 1.18 grams per milliliter. So percent by mass means that we need 19.5 grams of calcium chloride in 100 grams of solution. And we know we need 250 milliliters of it. I would recommend starting your dimensional analysis with the 250 milliliters. So 250.0 milliliters. We can convert that over to grams using the density. So we know that we have 1.18 grams in 1 milliliter of solution. So now we're in grams of solution. Then we can use our concentration as a conversion factor, because we know we need 19.5 grams of calcium chloride for every 100 grams of solution. And so if you cancel out units, we did milliliters. Now grams of solution, we're going to end up in grams of calcium chloride. So if I do that math, I get 57.5 grams of calcium chloride. And it says, how would you prepare? So I would weigh out 57.5 grams of calcium chloride, dissolve it in probably around 200 milliliters of water, and then bring it to 250 milliliters with more water. So again, I don't want to measure out 250 milliliters, then add my 57 grams to it. That's going to end up with a solution volume of more than 250 milliliters. So you can see 57.5, add enough water to be 250.0 milliliters total. Let's practice another one. Calculate the molality, so that's moles per kilogram of solvent, moles of solute. The molality of a solution made by dissolving 34.0 grams of ammonia in 2 times 10 to the third milliliters of water. So we want to know our moles of NH3, and we want to know our kilograms of H2O. So to find our moles, we're going to take our 34.0 grams NH3 times the fact that 1 mole of NH3 is 17.04 grams, and I get 1.995 moles of ammonia. Then my kilograms of water, I have 2.00 times 10 to the third milliliters times 1.00 grams in 1 milliliter times 1 kilogram is 1,000 grams. So my units all cancel, and I can find that I have 2.00 kilograms of water. So if I take my 1.995 moles of ammonia and divide it by my 2.00 kilograms of water, I find that I have a 1.00 molal solution. Another example, these units just become more familiar as you work through them. Again, I would recommend pausing before checking the solution here. If you can work it out yourself, then you don't have to listen to me talk it through. What is the molarity of a solution prepared by mixing 17.2 grams of C2H6O2 with 0.5 kilograms of water to make 515 milliliters of solution? So this one is checking, do you understand what molarity is? And molarity is going to be my moles of C2H6O2 divided by my liters of solution. So to find my moles, I'm going to take my 17.2 grams C2H6O2, convert it over to moles, figure out my molar mass is 62 grams in 1 mole. So I have 0.277 moles. Then my total solution is 515 milliliters, which is 0.515 liters. So if I take my 0.277 moles divided by 0.515 liters, I find that my molarity is 0.539 molar. 0.538, that's close enough. Here's a table you might find useful. It's from your textbook. I'm not quite sure where. But it shows you how to convert between units of concentration and solution quantities. So you can find, your solute, your solvent, your mass, and then how all of these things are connected to each other. So if when you're doing questions converting from one unit to another, this table can be, or a flow chart really, can be a good help to you. More questions to work on. A solution of ammonia is made by dissolving 35 grams of ammonia in 90 grams of water. The density of the solution is 0.989 grams per milliliter. What is the molarity of the ammonia? All right, so we're looking for the molarity. So we need to know our moles of NH3, and we need to know our liters of solution. So to find our moles of ammonia, we're going to take our 35 grams. 1 mole of ammonia is roughly 17 grams. And so we have 2.06 moles of ammonia. Then we need to know our liters of solution. And to get there, we're going to find our mass of our solution by taking our 35 grams of ammonia plus our 90 grams of water, and that gets me 125 grams of solution. Then I can take my 125 grams times my density, 0.898 grams in a milliliter, and find that I have 139 milliliters, which is 0.139 liters. Then I can take my 2.06 moles divided by 0.139 liters and find my molarity of get an answer of 14.8, so 15 molar. All right. One other topic to talk about that's related to concentrations is the concentration of various chemicals. We're going to talk about the dirty dozen chemicals, which are persistent organic pollutants. Basically because they are fat soluble, they don't wash away in water. So in the U.S., the EPA monitors the levels of these toxins in drinking water. So let's do a little math here. How much dioxin, so here's dioxin, is safe for an adult to consume in 1 year. So the EPA maximum is 0.12345670 milligrams per liter. And we're assuming an adult drinks 715 liters of water in a year, which seems kind of low to me, but that's okay. So if we have 715 liters per year times 0.12345673 milligrams per liter, we can get our answer of 2.145 times 10 to the negative fifth milligrams. Now that comes into play on my next slide here, which is back in 2004, a presidential candidate in the Ukraine, Viktor Yushchenko, was poisoned with dioxin, specifically TCDD. So dioxin is kind of a category of toxins, and TCDD is a specific one. He measured a concentration of 108,000 picograms per gram of fat, which indicates a dose exceeding 2 milligrams. And we just calculated that the safe level for a human in a year is 2.145 times 10 to the minus fifth milligrams. So that is 1,000,000 times the yearly dose, the maximum yearly dose. So you can see if you compare these two pictures, we're not taken that far apart. It affected his skin. He had chloracne for many years, but he did survive and didn't have long-lasting symptoms. So just an example of where these units of concentration can come in handy if you understand them.